All right, have you ever really stopped to think about the magic happening inside your phone? I mean, the thing that connects that digital world to the actual physical world all around us. It's this silent, invisible process happening billions of times a second, and it literally makes our modern lives possible. Well, today, we're going to pull back the curtain on that very magic.
I mean, think about it. You tap a song on your phone, right? You're basically just poking at a file. It's nothing more than a long stream of ones and zeros. And yet, what comes out of your headphones is music, actual physical sound waves moving through the air. So how on earth does that digital data make the leap into our physical world? That's exactly what we're digging into today.
Okay, to really get this, you have to realize that we're basically living in two different worlds at the same time. You've got the rich, continuous world we experience with our senses, and then there's the super precise, numerical world that our technology lives in. Let's break down what that actually means.
So pretty much everything out there in nature is analog. The sound of your voice? That's not a list of numbers, it's a smooth, continuous wave. And the temperature outside doesn't just jump from 70 to 71 degrees, right? It flows through every single tiny value in between. But our gadgets, they don't think like that at all. They speak digital, which is a language made of separate, very precise numbers.
So if we have these two totally different languages, who are the translators? Well, let's meet the unsung heroes of, well, basically all modern electronics. The analog-to-digital converter, or ADC for short, and its partner, the digital-to-analog converter, the DAC. And trust me, whether you know it or not, you are using these things constantly.
All right, first up, the ADC. When you speak into your phone, the microphone captures your voice, an analog wave, and turns it into an analog electrical signal. The ADC's job is to jump in, take that smooth, continuous wave, and chop it up into a series of numbers. That's the digital data your phone can actually understand and send. It's literally taking reality and turning it into code.
And yeah, you guessed it, the DAC does the exact opposite. It takes that digital file, the ones and zeros of your favorite song, and it translates it back into a smooth analog electrical signal. That's the signal that then makes your speakers or headphones vibrate to create the real sound waves you can actually hear. It's turning that code right back into reality. Okay, but this brings up a really interesting question, doesn't it? If our world is analog, and we have to convert back to analog anyway to hear or see anything, why even bother with the digital part in the middle? I mean, why not just keep everything analog from start to finish?
Well, the answer all comes down to one big trade-off: fragility versus robustness. See, analog signals, they're natural, but they are super fragile. They pick up noise and interference like crazy. Think of the static on an old radio. And if you've ever copied a cassette tape, you know the copy never sounds as good as the original. But digital signals, they're just numbers. They are incredibly tough, mostly immune to noise, and you can copy, store, and send them a million times, and they will be absolutely perfect every single time.
Okay, so that's the why. But what about the how? How does a smooth, curvy analog wave actually get transformed into a bunch of blocky numbers? It might sound really complicated, but it actually boils down to just two main steps.
And those two key steps are called sampling and quantization. Basically, first we take a bunch of snapshots of the analog world, and second, we give a number to each one of those snapshots. Let's break down exactly how that works.
So step one is sampling. Imagine the ADC looking at that smooth analog wave. What it does is take a quick measurement, a snapshot, of the wave's value at thousands of perfectly regular moments, every single second. It's exactly like how a movie is just a series of still pictures shown really fast. And just like with a movie, the more samples, or frames you take, the more accurate your final representation is going to be. All right, then comes step two, quantization. For every single one of those snapshots we just took, the ADC has to give it a number. But here's the catch. It doesn't have an infinite range of numbers to pick from. It has a limited set of levels it's allowed to use. It's kind of like if you're measuring something with a ruler that only has inches marked on it, no half inches or anything. You just have to round to the nearest inch. That, in a nutshell, is quantization. Now, that idea of rounding is super important because it brings us to a really crucial point. This whole translation from analog to digital, well, it's not perfect.
And this really gets to the heart of it, because you're forcing this smooth, infinitely detailed signal into a limited, finite set of numerical steps. A little bit of the original information always gets lost in the process. The digital version is never, ever a perfect copy. It's always an approximation of the real thing.
So the big question becomes, how good is that approximation? Well, the accuracy of this conversion has a name. It's called resolution, and we measure it in bits. It's pretty simple. The more bits an ADC has, the more levels it has to work with, and the more accurate that final digital copy is going to be.
And the impact of adding more bits is just astonishing. For example, a really simple 3-bit converter only has 8 different levels to describe the signal. That's a super rough sketch. But if you jump to an 8-bit converter, suddenly you have 256 levels. Every single bit you add doubles the number of levels, which means the accuracy just shoots up exponentially.
And you can literally hear this difference in your everyday life. 8-bit resolution, that gives you that classic crunchy sound from old video games. 16-bit is what we think of as standard CD quality, which is pretty darn good. But professional recording studios, they use 24-bit resolution to get an incredibly detailed, high-fidelity sound. It's simple. More bits equals more realism.
You know this unavoidable little difference between the original smooth wave and its digital copy? That has a name too. It's called quantization error. If you could zoom way, way in, the digital signal wouldn't look like a smooth curve at all. It would look like a staircase where each step is one of those distinct numerical levels. The whole goal of high-resolution audio is to make those steps so incredibly tiny that our ears just can't tell the difference.
So when you step back and look at it, it's pretty clear that these tiny little translators, the ADCs and DACs, are really the unseen engines driving our modern world. They're constantly building and rebuilding that bridge between the physical and the digital.
All right, so let's just quickly recap the big ideas here. First, our world is analog, but our gadgets are digital. Second, to bridge that gap, we absolutely need those translators, ADCs and DACs. Third, we do all this because digital is tough and reliable, even if the translation itself is imperfect. And finally, the key to a better translation, a better experience, is higher resolution. More bits means higher fidelity. Simple as that.
And that kind of leaves us with one last thing to think about. This bridge between analog and digital, it's already everywhere. It's in the smartwatch tracking your heartbeat, the sensors in your car, the smart devices in your home. So as this technology gets even faster, even more precise, where else is this bridge going to take us? What new pieces of our physical world are we going to bring over into the digital realm next?